All right, good morning. We are continuing with electric potential. And we'll do a, what do we do? A cylindrical charge distribution, finding the electric potential everywhere, maybe a spherical one. And then you'll continue to practice those over the weekend. So let's start off with this worksheet. It says we have a large region of space that has a uniform electric field in the plus x direction. In the diagram below, we show equipotential lines for this field. At the point 0, 0, the origin, the electric field is 30 newtons per coulomb in the x direction. And the potential is 100 volts. It says rank from greatest to least the strength, the magnitude of the electric force on a plus 5 coulomb charge when it's placed at each of the following locations. So we want to know the force, the magnitude of the force on that charge placed at each of those locations. Maybe you should draw the electric field first. Draw the electric field lines. So our equipotential lines look like this. What would the electric field lines look like? And they tell us actually too, right? Yeah, they have to be perpendicular to this. So you know they either go this way or they go this way, right? One or the other. But they told us it was a uniform electric field pointing in the positive x direction. So we'll just draw them in that direction. What if this was my, what if these were my equipotential lines? Okay, so equipotential surfaces are always perpendicular to electric field lines, or vice versa. Electric field lines are always perpendicular to equipotential surfaces. And electric field always points toward lower electric potential. So the electric field lines in this case would be something like this, right? So maybe there's a negative charge in there. Okay, back to this problem. What's the force on a +5 Coulomb charge when you stick it at one of those locations, and how's it different from the force if you stick it at a different location? This is the easy one. I'm starting you off with the easy question. What's the electric field at the origin? $30. What's the electric field at point E? $30. What's the electric field at point F? $30. Because the electric field is uniform. It's the same everywhere. Okay, now answer the question. What's force? Force is Q times E, right? If the field is the same everywhere, the force is the same everywhere. Doesn't matter where you put that particle, it experiences the same force. The electric potential is different, yes. Not the force between charges. There's only one charge, right? There's an electric field that exists in this region of space, and we're taking a charge and we're putting it here and saying, what's the force on it? And then we're moving that charge over here, we're saying, what's the force on it? And then we're moving it over here, we're saying, what's the force on it? due to the field that already existed in that region of space. So you have to think about the electric field lines, right? The electric field lines look like this, right? I just drew them here. Those electric field lines are parallel to each other. What does that mean? That means the electric field is not changing. The electric field lines are drawn where they're most dense. The electric field is the strongest, right? So over here, the lines are close together, right? I draw a circle over here. I've got 1, 2, 3 electric field lines. I draw that same circle out here, and maybe I have 1, maybe I have 0, right? So the density of the field lines is much less at position 2 than at position 1 there. So the electric field is weaker at position 2. It's not as strong. If I put a charge over here, it feels a much smaller force than if I put the same charge over here where the electric field is very strong. But over here, I draw a circle, and I draw a circle over here, and I draw a circle over here. They all have the same density of field lines. Doesn't matter if I put the charge there or there or there. The force is the same regardless. Okay. Now, now let's get into electric potential. So next question is, if the equipotential lines are spaced 1 meter apart, find the value of each equipotential line. They shouldn't call them lines, they're surfaces, but that's okay. Each surface. You need to see the picture again. They are separated by 1 meter. Okay, we do not use KQ over R. KQ over R is the electric potential near a point charge. So we don't know what charges are creating this charge district, this electric field, but we know it's not a point charge because the electric field wouldn't be uniform, right? It would be more like this one on the right. It's probably an infinite sheet of charge or something like that, but we don't care. What we care about is we know the electric field in this region of space, and we know the distance. And so we can tell if the electric field, we know this equation is always true. And if the electric field is constant, well, it comes out of the integral, right? And the electric field's constant here. So the electric field is 30. The distance is 1 meter. So 30 times 1 is 30. So delta V between lines, 30 volts. Okay, so go ahead and fill them in. What are they? So it was given, what was given that you have to start, all we know are delta V's, right? All we know are changes in electric potential. So you have to start with where you know the potential is. Otherwise, we'd all have different answers. They'd all be correct, but they'd all be different, right? So where is it given? It's given that it's 100 volts at the origin, right? Okay, so now what do we know? If we know that these lines are 30 volts apart, and we do, and it's 100 volts at the origin, what's the one to the left of it over here at x equals -1 meter? Has to be 30 volts higher because we're going opposite the direction of the electric field. This one has to be 130, and this one over here left to the left of that has to be 160. Now let's go in the other direction. Okay, so over here, what do we have? X equals 1 meter, 70 volts. X equals 2 meters, what do we have? 40. X equals 3 meters. What's the next one? And the next one. Okay, that's a 5. So these, we know that they differ by 30 volts because we did the integral of E dot ds. When E is constant, it's just the electric field times the distance that gives us the electric potential, the change in electric potential. But change, so we knew each one of these lines had to be 30 volts apart. But we have to know where to start, right? All we know are differences. So we look and see in the problem, it says at the origin, it's 100 volts. So now we know when we go in the direction of the electric field, we have to be going to lower electric potential, lower voltage. So we subtract as we go to the right, which is in the direction of the electric field. We add when we go opposite the direction of the electric field. This d is the distance that we're moving to get this delta v. If delta v is the delta v between x equals 2 meters and x equals 3 meters, then this d is the distance between x equals 2 and x equals 3, which would be 1 meter. If delta v is the distance between this point and this point, then d would be the distance between those 2 points. It's whatever the delta v is. It's the distance between the 2 points that are giving us our delta v. Negative voltage. It means it's less than 0. Right? It's voltage is a scalar. So negative numbers are less than positive numbers. So when we're moving, we can define 0 to be anywhere. It's kind of like gravitational potential energy, right? When we were doing problems, maybe you picked the floor to be 0 gravitational energy. And then when you're at the table, you're 1 meter higher than that, right? When you're above the table surface, you're higher than that. When you're at the ceiling, you're even higher, right? Maybe I picked 0 to be the table. So if my object is between the table and the floor, it has to have negative potential energy, right? Maybe we pick the ceiling to be 0. And when our object gets closer to the center of the earth, it has to have less than whatever it started with up here. Gravitational energy has to go down as you get closer to the center of the earth. So if you define 0 to be here, it has to be some negative value. It has to be less than 0. That's all it means. It's the same with voltage. We can define 0 to be anywhere. If we define 0 to be the origin, and we go to the right, we know we have to be less than 0 because we're going in the direction of the electric field. So this would be negative 30. And if we went to the left, it would be positive 30 over here. It's just a number, right? It's a number that's less than 0. Yeah, good stuff. Yeah, it would just keep going until the electric field changed. As long as the electric field is uniform as it goes out towards infinity, then the potential would just keep changing until we got to infinity. Okay, be ready for number 2. That was number 1. What's the direction of the force on an electron if it's placed at rest at C? Electron. Somebody didn't have their coffee this morning. Man, we are off to a slow start today. Okay, an electron, the electric field points to the right. So an electron would go the opposite direction, to the left. All right. What's the direction of the force on an electron placed at A? To the left, right? What is it, the force on an electron placed at any location? To the left, right? Correct? Because it's a uniform electric field. The electric field is the same everywhere. No matter where we put that electron, it's going to experience the exact same force, opposite the direction of the electric field because it's a negative charge. All right, let's move on to so it's the same everywhere, right? The force is the same everywhere. How about a proton placed at position A? To the right, all right. Proton's positive, it goes in the direction of the electric field, okay. Same at position F, okay. Which location is the force on the proton the greatest? It's the same everywhere, right? Okay. How about if we put an electron at point A with some initial velocity in the x direction? What would the direction of the force be? To the left. What if we took that electron at position A and gave it some initial velocity in the negative y direction? What direction is the force? To the left. It doesn't matter. Velocity doesn't matter, right? It's F equals QE. If the electric field points to the right and Q is positive, then the force also points in the same direction as the electric field, to the right. If the electric field points to the right and Q is negative, then that flips the direction for the force. It points to the left. There's no mention of velocity here. It does not matter. We don't care if it's moving or if it's at rest or what direction it's moving. At that instant, the force is to the left. Okay, we good with this one? In case you want to go back later and take a look at these. Okay, let's move on. So what we want to do is use delta V is minus the integral of E dot ds and Gauss's law to find okay, so we've got an infinite length cylinder. It's a conductor. Radius capital R. Some positive charge distribution. And we're given that V equals 0 at R equals the radius of the cylinder. Okay, so that's our given information. We are going to find the electric potential everywhere. So remember, we have two techniques, just like finding electric fields. We have two techniques, right? One, integrate over the charge distribution to find the electric field. Two, look for symmetry, spherical, cylindrical, or infinite sheets. If you have one of those symmetries, you use Gauss's law. It's much simpler to find the electric field, right? Now we have to find electric potential. So we have the kind of the same two techniques. We could integrate over the charge distribution, or if we know we have one of these symmetries and we can find the electric field really easily using Gauss's law, then we can use the integral of E dot ds to get delta V. So that's what we'll do here. So first, let's do first we need to find E everywhere. Just when you thought you could forget about Gauss's law until the final, you can't. You're going to need it for this exam. So find E everywhere. So let's do that. We have a spherical, we don't have a spherical. We have a cylindrical charge distribution, radius R. It has positive charge. It's a conductor. A week from today, right? So the next exam, Friday, a week from today. I keep you on your toes. Okay, so our charge distribution looks something like this, right? So what's our electric field for R? Less than the radius, inside. If we were inside this cylinder, what would the electric field be? 0, because the cylinder is a conductor. Okay, so where does all this charge end up? Even if we could reach in magically with some kind of a charge injector and put all the excess charge at the center, where's it going to end up? On the outermost surface, right? Because a conductor, the charges are free to move and they repel each other. They're going to end up on the outermost surface. So all the charge is on the outermost surface. If I did some kind of a Gaussian surface inside, there would be no charge in there, so there's no electric field. And we're inside of a conductor, right? So you know it's going to be 0 in there. E equals 0. Now let's do it outside. So we'll draw a Gaussian surface. We'll match the symmetry of the problem. We've got electric field lines that are doing something like this, right? And we say the integral around all of the surfaces that make up our enclosed Gaussian shape there, this imaginary red cylinder we're putting into our problem, of E dot dA has to be the Q inside of that cylinder over our constant epsilon naught. So I can split this into 3 integrals, right? The integral over the top, the integral over the bottom, and the integral over the side of my cylinder. So this is the integral top plus the integral over the curved side. plus the integral over the bottom is q in over epsilon naught. And the integral over the top and the bottom of E dot dA are going to be 0. Because you can see the field lines are coming out and they're not penetrating the surface, right? So the dot product gives us 0 there. So what do we get? We get E times the area of the side is Q in over epsilon naught. The area of the side, that says side, is 2 pi r h, where h is this distance here. The height of our cylinder. And what is Q in? Q in is the charge per unit length times the length. And so the h's cancel, and I end up with, and I end up with E is some constants times our charge density over R. And in this case, it points outward, right? In the R hat direction, because we're talking radial symmetry here. We're using cylindrical coordinates. So make sure your direction makes sense. I had so many people tell me on the exam problem, we were finding the electric field at the origin due to a charge somewhere, right? And the electric field at the origin. What direction is the electric field at the origin due to that charge? That way. So how would you write that on an exam? The electric field is KQ over R squared. This is R, let's say. What direction? I had a lot of people that called that the R hat direction. What direction is radially outward from the origin? I don't know. It means nothing to me, right? This is an XY grid. In fact, I think it was labeled X and Y. This is the minus I hat direction or minus X hat. I don't care which one you use, right? It's to the left, or you could write to the left. Don't write minus to the left, though. I don't know what that means, okay? So make sure your direction makes sense with what's given, what the geometry of the situation is. So I'm just writing here radially outward, but I could put an R hat there, right? That R hat means radially outward. Okay, enough of that. Let's move on. So we've got our electric field. We've got our electric field everywhere. Now we're ready to find electric potential. So now we use the change in potential is minus the integral of E dot ds. So where are we going to start? This gives us the change in potential. So if we start where we don't know what the potential is, we'll get the change going to somewhere else, but it won't tell us what the potential is there. So we always start where we know what the potential is. So in this case, V is 0 at the radius of the cylinder. And with cylindrical symmetry, it's almost always on one of the cylinder surfaces. Okay, if you have multiple cylinders, it could be any one of them, but it's almost always on one of the surfaces of the cylinders. For spherical symmetry, it's almost always at infinity, v equals 0 to infinity, because that's where it naturally goes to 0. And you'll see that it naturally goes to 0 on the surface. You'll see that in a minute. Okay, so what are we going to do? Let's find, let's go outside. Let's do the outside first, the r greater than the radius of our cylinder. So our cylinder's here. This is, and we're going to start here. This is going to be our initial point. And we're going to move out here to some final location. Right? This is capital R, and this is any R. I just use lowercase r to be any arbitrary distance, and I'll leave that way in my equation so I can find it, right? If I want to know 1 meter from the axis of the cylinder, I can plug in r equals 1 meter. If I want to know 10 meters, I can plug in r equals 10. I'll just leave it as a function of r. So delta v, let's start, minus the integral, E dot ds. There's our equation. What is delta v? It's final minus initial. What is the electric field? It's our constant, 1 over 2 pi epsilon naught, lambda over r. Then we have a dr, and then we have a cosine theta. Theta is the angle between the electric field and our dr. And so we're going in this direction, and our electric field points in this direction. So we get a 0-degree angle there. Like they point in the same direction, E and dr. And my integral goes from r initial to r final. You always put the smaller number at the bottom. In this case, it happens to be the initial. But if we were going the other direction from final, if we were going inward, we would put r final here and r initial here, because r final is smaller, right? When you do an integral, you always put the smaller number at the bottom. So this would be from capital R to lowercase r, any arbitrary r, right?
Can we just find out if it's positive or negative in the end of the equation?
We will do that. So this is what I do. I try to get the minus sign. You see there's a lot of minus signs, right? You have to get the order of the integrals right, of the integration right, the limits. You have to get the cosine right from the dot product, right? You have this minus sign out in front. You have lots of stuff going on here. It's tricky sometimes. I try to get it right. You know, I've gotten pretty good at it over the years. Usually I get it right. But at the end, I check it and make sure. If I'm wrong, I just add a minus sign and say this needs to be negative or this needs to be positive. Okay?
Okay.
All right, so what we're going to do now is say, oh, wait a minute. We know V initial. It's 0. We're starting at 0, right? So this tells us that V final is equal to, we can start to do our integration. Well, we can pull out our constants, right? What happened? So lambda is a constant. It comes out also. Lambda over 2 pi epsilon naught. And this is just the integral of 1 over r, right? And we know that this, now we can, well, let's finish our integral first. And then at the end, we'll check the signs. That's just a natural log of r. And that is the natural log of r over r, right? Because the natural log of a minus the natural log of b is the natural log of a over b. Okay, so now we check our signs, right? So this one, what does v final have to be? I hate when it does that. Things just disappear sometimes. Okay, so what direction does our electric field point? Points radially outward, right? And if we start at 0 and we go in the direction of the electric field, what does our V have to be at the end? Good. Okay. Negative. We're starting at 0. We're moving in the direction of the electric field. Electric field always points toward lower potential. What's lower than 0? A negative number. Okay, so then we come back over here. This is positive. This is negative. So what about this guy? If lowercase r is bigger than capital R, the natural log of a number bigger than 1 is positive. If lowercase r is less than capital R, the natural log of a number smaller than 1 is negative. In this case, we're outside of the radius of the cylinder. So little r is bigger than lowercase r is bigger than capital R. So this is positive. So the whole thing over here is negative, so we're good. If it was wrong, I would just throw a minus sign in there and say, now it's right. Okay? So what's my answer? My answer is right there. V final is equal to, this is V at any R, negative lambda over 2 pi epsilon naught, natural log of R over R. So you see why we set the 0 to be the radius of the cylinder? Because we have a natural log of something over the radius of the cylinder. So if we plug in lowercase r equals capital R, we get the natural log of 1, which is 0. It naturally goes to 0 on the surface at the radius of one of the cylinders. Now we'll go inside real quickly. R less than the radius of our cylinder. So we're starting here, and our final is going to be here somewhere, right? So this is R, and this is capital R, right? So we say delta V is negative the integral of E dot ds. This is going to be V final minus V initial. What is E in here? 0. So delta V has to be 0. Now V does not have to be 0. The change, delta V, has to be 0. V just has to be constant. So whatever V is on the surface of that cylinder, it has to be the same all the way through that cylinder because there's no electric field in there. It can't change the potential. So it just happens, in this case, it happens to be 0 at the surface. So because this is 0, then V final is also 0. But V does not have to be 0 inside of a conductor or any place where the electric field is 0. It just has to be constant. Delta V has to be 0. Okay. So practice that. I think we did one. We'll do a spherical symmetry problem. So here's a cylindrical one. We'll do spherical next time. I think we did something with spherical already. And then think about what happens when you get shapes inside of shapes. You know, so you can have a cylinder inside of a cylinder or a sphere inside of a sphere. There's a couple of problems in the book like that. So you have to keep integrating. Every time you get to a boundary where the electric field changes, you have to stop and then start again, do the equation again, because your electric field is different. So this equation right here, you're going to use that in some region of space where you know what the electric field is, and you can get right up to the boundary. You can figure out what the potential is there. And then if the electric field changes in the next region of space, like going through a shell or something, so you have E1 over here, and then this is a conductor. So you have E equals 0 here, and then you have E2 here, right? You have different fields. So if you're finding the electric field if you're finding the electric potential everywhere, you start maybe V equals 0 at infinity. You start there and you work your way in until you get to this point. And then you start again. You start here because now you know what the potential is here, and you work your way in until you get to this point. And then you stop there and you work your way in, because you have to break up this integral only works where you know what the electric field is. So every time the electric field changes, you have to stop and reboot. Okay, so exam 1 solutions are under the lecture notes. They're all by date, so I put them on the date of the exam. So if you look, lecture notes are all by date in order. So on the date of the exam, there's one that says exam solutions. All right, I'm going to stop the recording. I'll stick around for a few minutes.